Well, welcome Earth Space Sciences class. Today we're going to do a little video lecture on earthquakes. And so to start it off, I normally would ask the class, where on Earth do people have to worry a lot about earthquakes? And very commonly, the first response would be California. And that is certainly the case. There were two of you in class that were in California and experienced an earthquake there. Interestingly enough, that's not the most seismic or earthquake-prone state in the United States. Number one would be Alaska. Other places around the world that are very earthquake-prone would include, if we look at this map here, actually if we go to the United States first, yeah, we've got California, we've got Alaska. Up here near Seattle, Portland, Oregon, there is a lot of earthquake possibility there, which a lot of people aren't familiar with. Around Yellowstone, you bet. Here in southern Missouri, this one in Yellowstone, here, we'll start with Seattle. There's what's called the Juan de Fuca plate up here that's crashing into the North American plate, subducting under it, making earthquake potential. It's believed that may be the end of what was called the Farallon plate, which is kind of subducting under all of North America, with the exception of that little tail sticking out here yet. And it's kind of gone shallow underneath North America, scraping along underneath the North American plate and maybe causing these earthquakes here and the Rocky Mountains. There's not a good explanation well, there is, but I mean, southern Missouri here is an earthquake-prone area as well, because this is the remnant of a failed rift, a crack in North America. North America tried to tear apart like Africa is doing, from the Keweenaw down through Iowa, and this is another remnant of it that still has some energy here in southern Missouri. And there's a video clip I'm going to show you that talks about an earthquake here. Charleston, South Carolina is another. If we go around the world, yeah, Hawaii, Puerto Rico. Hawaii, because of the movement of magma underneath that volcano, again, not near a plate edge. Puerto Rico is. Around the world, well, we just talked about the west coast of South America, because the Nazca plate is crashing headlong into South America, making those. Another subduction zone here along Central America, Mexico, Guatemala, Honduras, El Salvador, those places, earthquake prone. This is Iran and Pakistan, India, Nepal, Indonesia, of course, Japan here. This is Kamchatka Peninsula of Russia. All very earthquake-prone areas. And if we look at that in connection to a map, it should make some sense. So here's that Juan de Fuca plate slamming into northern part of United States. Here is North America slamming into the Pacific plate, making the earthquake-prone area in California, and same in Alaska. Here's Japan, complex. Look at all the plate edges there. And the same here with Indonesia. It kind of goes off the map. This is Indonesia. Here is Iran, right here, plate edge. India, right here, plate edge. And South America already made that case. So very often, earthquakes are associated with plate edges where subduction is occurring. We looked at this area in lab, and you know the Pacific plate is crashing headlong into the Australian plate here and making places where earthquakes occur. Of course, here is Missouri. That's an intraplate earthquake, as is Hawaii, which have their own unique reasons for being. Okay, so those are places around the world that are prone to having earthquake problems, and notice the association with plate boundaries, with the edges of tectonic plates. So this was San Francisco in 1906, hit with an 8.3, 8.4 magnitude earthquake, I believe somewhere in that ballpark, and it pretty well wrecked the city. This is what it looked like after the earthquake, and this was City Hall. But they didn't portray the big problem with the destruction of San Francisco in 1906 as an earthquake problem. They portrayed it as a fire problem. After the earthquake, people were, living out in the streets because they don't want to be in these buildings that were wrecked by earthquakes, and they're building cooking fires and heating fires, and basically caught the city on fire. And it burned, all that debris burned, and so they talked about the Great Fire of San Francisco, not the Great Earthquake, so that people weren't scared away from San Francisco. Kind of interesting. But other recent earthquakes that have been a problem would include, well, here's some images. Actually, I'm going to scroll this back up. Here is Haiti in 2010. If we look at Haiti, that makes some sense. Here is the Hispaniola. This would be the Dominican Republic. This would be Haiti, this portion here. This is the Caribbean plate going east, slamming headlong into the North American plate, which starts here at the Mid-Atlantic Ridge and goes that way. So this would be what we would call a transform boundary, as the North American plate's moving that way, and the smaller Caribbean plate is moving that way. And Haiti is actually at double risk because there's a fault here on the north of the country, fault here at the south of the country. And so you got Jamaica, Puerto Rico, obviously also at risk. The most recent earthquake occurred right here out on this peninsula a little farther. In 2010, one occurred back here, closer to Port-au-Prince, which is right here. And because there were so many more people near that earthquake, there was a lot greater loss of life, somewhere in the area of 250,000 people or more. And the big issue was building collapse. Look at all those, poorly constructed buildings. They're poor people, so they can't make well-constructed buildings. Kathmandu, Nepal, north between India and China. We've already talked about that. This was 2015, magnitude 7.8 earthquake. Big problem. This is the Indonesian earthquake of 2004. And this is the other thing that kills so many people in an earthquake. When you have the right kind of movement in the two plates that move, creating the earthquake, you can create a tsunami or tidal wave. And this 2004 earthquake created a big one. It washed over, this I think is Banda Aceh. It's like a north part of Sumatra, that north island of Indonesia. The tidal wave hit this, washed over, it just obliterated the island. And I'm going to have you look at a clip of the tsunami that hit Japan in the most recent earthquake there. Of course, roadways, as the earthquake shakes, it can turn the soil to behave more like a liquid, and it actually moves. And in this case, it wrecked a road doing that. Here, the earthquake energy waves knocked over a roadway. And then this image here, I want you to remember this. I'll refer to it again, because the rails here actually captured the motion of an earthquake wave as it moved along the rail, and then as it moved past, the rail was kind of frozen in the way that the earthquake wave moved, kind of like a sidewinder snake. Okay, so when we think of earthquakes, we think of the fault, and this is a fault in the Quincy mine in northern Michigan. It's a copper mine. You can kind of see a coppery color there, and this is a crack. So here's one piece of Earth's crust, and it wants to move up and over, and here's the other piece, and it's going to move down and under if it can. And so this is the actual contact point between those two rock masses. Incredible to think of the pressure that must exist there. And so this rock mass is trying to move down while this rock mass is trying to move up and over. And so the rocks would catch at a point. And I tried to describe that yesterday on Tuesday in class. So if this were the catch point, the pressure trying to move this rock would still continue that way. And the pressure, the forces trying to move this rock down and under would still continue. But they couldn't move because they were caught here. And so the rock at that contact point, if this were it, would have two choices. That rock, if it were made out of the right kind of minerals, could bend and sort of release energy slowly and not really create an earthquake. But more typically, that rock will resist the movement of the plates until it can no longer take it anymore, and then bang, it breaks, and this plate jumps up that way, and this plate down that way. You can see tens of feet of movement in plates instantaneously is what can happen in an earthquake, and really cause a lot of damage and release a lot of energy that causes damage. So when we think about these things we call faults, there are different ways that they can occur. Actually, I'm going to scroll this back up to the top. If you have plates that are stretching, one moving this way and one moving this way, you'll have what's called a normal fault. I don't know what makes it normal, but that's what it's called. And so in this instance, because the crust is stretching, This block drops down, and this block, because there's a lot of hot underneath it, might rise up and create this sort of a look. Now, those words, Horst and Graben, Graben is ditch, German for ditch. Horst is German for heap. And basically the Horst is the uplifted block. Graben is the down fallen block, if you will. So that's a normal fault. And this is Kenya, where that actually is happening. And get that sort of stair-step look to things as the blocks move one relative to the other. A reverse fault or thrust fault, I'm going to use those terms interchangeably, occurs when the plates move the opposite direction, when they move together in a convergent fashion. So in this image, this plate wants to crash into this one and then move up. This one crashes in and moves down. And the only difference between a reverse fault and a thrust fault is this angle here. So we're not going to get hung up in that. So this is a reverse fault. So this piece of crust used to be connected to this down here, and it made that sort of a look. So that's a reverse fault. Here's a thrust fault. You can see it's just a steeper angle is all. And when you look at that, here's a place where that would occur. You can also have two plates moving past each other in opposite directions. We would call that a strike-slip fault. Now, tsunamis are created in this sort of a scenario where you have one block that shoots up and another block that shoots down. If this happens underneath the ocean, this can displace a lot of water and create a tsunami. Now, I want to pause right here, and I'm going to have you pause the video, and I will put a link to the Japanese tsunami, earthquake and tsunami, and you're going to see that wave out in the deep ocean, or out offshore, I should say, and it's actually sets of waves, and a very excited talking Japanese person on there. But then watch towards the end of the video, and it will show the wave actually hitting the shoreline, destroying a town and running inland. And that's the big question: how far inland will they run? I think with the Japan earthquake, the tsunami ran 6 miles inland, and I think it ran up, well, they said wave heights of 35 to 45 feet, but then when they hit the shoreline, sometimes they washed up to over 100 feet up on the shoreline. And so just you pause the video, go look at that clip, and then you can resume the video. Okay, so that's a reverse or thrust fault, creates tsunamis. A strike-slip fault, if it occurs under the ocean, is not likely to create as much of a tsunami because it's not going to displace vertically much water. The crust is moving horizontally, side to side, and it's not going to displace as much water. The San Andreas fault, which I showed you before, actually makes a surface feature, and we'll just look at a sort of a larger image of it right here. So here you have the North American plate moving west and the Pacific plate moving northwest. And so not directly together, not directly apart, not horizontal, but kind of at an angle. And so we would call that a transform fault. And so those are the different types of faults that there are: normal, reverse, strike, slip, oblique, yeah. If we're thinking about where an earthquake actually occurs, there are two terms. There's the spot where the rock has caught and actually broken. And if you go with the analogy, I was saying that if this is the spot where the rock actually caught and resisted movement and then eventually broke loose because the forces trying to move the one piece of rock relative to the other continue, we would call that the focus of the earthquake. That was the little colored dots that you dealt with in lab on Tuesday, okay, in class on Tuesday. Those are earthquake foci, where the earthquake actually happened. It doesn't happen necessarily all along this fault. There tends to be one spot where that break occurs and releases energy. If you go directly above that to the surface, you have what's called the epicenter. And this is often given a name of some city or geographic feature. So we would have, for instance, the Loma Prieta earthquake, the San Fernando earthquake, New Madrid earthquake, those sorts of things. When it comes to how earthquakes are assessed or evaluated, we're going to look at what used to be we used to talk exclusively about the Richter scale, but that was developed just for earthquakes within 100 miles of basically Los Angeles, given that rock type. It still is useful, but now we talk about the magnitude moment scale, and it's a similar concept. Now, in this diagram right here, this is a artist's rendition of a seismograph. Okay, and so here you have a weighted pen, and here you have a scroll of paper. And what I want you to realize is when an earthquake hits this contraption, the energy will be recorded on the paper. And so the bigger the squiggles, the bigger the earthquake. Well, what I want you to realize is it's not the pen moving on the paper that's making the squiggles. No. Actually, the paper and its base are all bolted right to bedrock. This whole base and the paper are bolted to bedrock. And the pen then is suspended with a spring to resist movement. So the pen is held still, and it's the paper that moves back and forth underneath it. That's how a seismograph actually works. Okay, so looking at some other seismograms, here's another look at the same sort of deal, maybe a nicer picture. But nowadays, of course, we have chart recorders that record data from some remote station that actually sensed ground movement and gives us the same idea. It's the same idea. The bigger the squiggle, the bigger the earthquake. Now, in class on Thursday, we're going to be dealing with some types of waves that earthquakes generate. We're going to call them P and S waves, which we're going to also call body waves, and then surface waves, which we're going to subdivide into Love and Rayleigh waves. This is what a seismograph might look like, and this is the arrival of the P wave, then the arrival of the S wave, and then there would be body waves down here. That'll have more meaning when we get into dealing with actual events. But what you end up with is a logarithmic scale. This is good, but I want to show you maybe a better impression of it. It's logarithmic, so in actuality, you couldn't show this on an image and still have it visible. A 9 is so much bigger than an 8 that it would go right off the scale. And magnitude 10, we just don't know of rock that could withstand Earth movement sufficiently to create a magnitude 10 earthquake. But you might ask, what's the biggest earthquake we know of? That occurred in 1960 in Chile. It was a magnitude 9.5 or 9.6. Number 2 all time, Alaska, 9.2 in 64. Number 3, Japan, 2011, it was a magnitude 9. Folks, you got to realize most of the most severe earthquakes that have ever occurred in recorded history have occurred recently. This is all in my lifetime. So while it flat out seems that Earth's generating more severe earthquakes now than it has in the past, which is kind of a scary thing. So this magnitude scale then is, as I said, is logarithmic. And what that means is when you go from a 6 to a 7, you're basically releasing 32 times the energy in a 7 that you do in a 6. But since it's logarithmic, if you go from a 6 to an 8, it's not 32 plus 32, it's 32 times 32, or over 1,000 times the energy is released in an 8 when compared to a 6. That's why it's hard to imagine a 10. Just don't know if that could even occur. Well, there's another way to evaluate earthquakes, and it's based on intensity, and this is subjective. That means it depends both on it's more subjective, both on objective data like damage done to buildings, but also subjective data like people's reactions to it. How afraid were you? Did you run outside screaming, or did you just sit inside and worry? That kind of thing. And this is something that we can use, this intensity scale. It's called the modified Mercalli scale to actually evaluate earthquakes in antiquity. For instance, the one that shook Paul and Silas out of jail in Acts. We can look at that and build Roman building or Jewish building techniques and materials at the time, the damage that was described, people's reactions to it, like the jailer, and get an idea for how intense that earthquake was. It goes from 1 to 12, and I will have a clip on Moodle that I would like you to stop and watch now. that involves the New Madrid earthquake, that one in southern Missouri that happened in the early 1800s and was the largest intensity scale earthquake that we know of. Okay, then just to finish up, I've already mentioned that there are earthquake waves. I'm going to demonstrate them in class on Thursday. You can look in your notes and see they're listed as well, we start off talking about all the waves in all the world. If you've had the physics, you've talked about transverse or shear waves and longitudinal or compression waves. And so a subset under that would be earthquake waves, seismic waves. And we subdivide any wave that an earthquake produces into two categories. Body waves, those are waves that are produced at the focus. And surface waves, those are waves that are produced at the epicenter. And of the body waves, ones produced down here, there are P and S waves. P waves are primary, and they're fast, on the order of 14,000 miles an hour. And the S waves are a little slower, on the order of 7,000 miles an hour, a little bit less than. If we go back to here, you can see the P waves arrive at a sensing station first, and the S waves arrive at that sensing station later. And it's the distance between these we're going to be paying attention to in the activity. Then there are also surface waves, and those are the ones that are produced at the epicenter. So when that energy reaches the surface, it transforms, it creates surface waves. And one is called a Love wave, which was captured in the railroad right here, kind of a sidewinder look. And the other is a Rayleigh wave, kind of like a water wave that kind of rolls. And these are the waves that do the most damage in an earthquake. These are the ones that create the problems. And we'll talk a little bit more about them in class on Thursday. Well, I think that's where I'm going to stop things for right now. Thank you and have a good day.